Hello, everyone. Thank you for joining us today for Lunch in Pompeii, a speaker series brought to you by the College of Sciences at the University of Central Florida and in partnership with the Orlando Science Center. My name is Brandon Landman. I'm the Vice President of Visitor Experience for the Orlando Science Center, and I'm very excited to present to you Pompeii, the Immortal City. Every 5 years or so, the Science Center brings in a blockbuster exhibit to bring to our community and to have exciting opportunities to learn about cultures, science, technologies from around the world. Pompeii is the perfect experience for these times. Timed entry creates limited capacity for our exhibit experience. On top of that, we also have ample space in our 10,000 square foot exhibit hall for you to wander and explore all the amazing artifacts that you're going to find. We chose Pompeii, the Immortal City because of the amazing stories that it has, and its connection to today is just more relevant than you would ever know. The science, the technology, the engineering, the mathematics, the STEM content that takes place in Rome and Italy 2,000 years ago is so relevant to today, from urban planning to plumbing, to glassworking, to metalworking, to measurements. It's all there. And we get to learn from that experience and explore that experience in detail that you've never seen before. Pompeii, the Immortal City is funded in part by Orange County government through the Arts and Cultural Affairs Blockbuster program and its tourism partners. Thanks to their support, we were able to bring this once-in-a-lifetime experience to our community, and we're able to offer free admission to our members. Pompeii will be with us until January 24th, 2021. We're the final stop in the United States. You won't be able to see this at any other time. Unless you go to Italy. So stop in, get your tickets, enjoy the experience, and come explore the amazing Pompeii, the Immortal City. Thank you for your support and enjoy today's presentation.
Well, hello everyone, and welcome to our fourth and final Lunch in Pompeii, presented by UCF College of Sciences and Orlando Science Center. My name is Jesse Zito, and I'm the Director of Programs here at the Orlando Science Center. We're excited to offer this opportunity again, and I'm so happy to see the response we've gotten for the speaker series. Orlando Science Center officially opened Pompeii, the Immortal City in October of 2020, and I'd encourage everyone to visit Orlando Science Center for your last chance to see these incredible artifacts up close before Pompeii closes on January 24th. Today's presentation will be followed by a Q&A session, so stick around to the end. You're welcome to submit questions. We'd really encourage you to submit those great questions during the presentation using the Q&A feature on your screen. We'd also love to know if any classrooms are out there watching the presentation, so let us know if you're a classroom. Today we have a fascinating presentation from Dr. Matthieu Baudelet. Thank you very much for joining us. Dr. Baudelet graduated with a BS in physics from the University of Lille in France in 2003, starting his experience in spectroscopy with Fourier transform microwave spectroscopy. In 2005, he graduated with an MS in laser and spectroscopy from the University of Lyon in France, and continued to complete his PhD in Lyon, working on laser-induced plasma and spectroscopic analysis. Very interesting work. Now assistant professor of chemistry at the National Center for Forensic Science, Dr. Baudelet's research focuses on the application of laser-based spectroscopy for forensic analysis. A large part of his research focuses on the quantification of interferences in spectroscopic signals. Thank you very much for being here today, Dr. Baudelet. This is a field of science that I don't know that much about, and I'm so excited for your presentation today. You feel good? Are you ready?
Yeah, I think it's good. Yeah, thank you.
All right. Yeah, well, thank you for joining us, and I'm going to send it over to you to start whenever you're ready.
All right, well, I'm going to share the screen then, and share. Here we go. Everything is good. All right, well, thank you first for the invitation. That was really a great pleasure when I got the invitation. And so here, what I want to talk about is maybe a little bit different from the three first presentations that were more about the archaeology and the life, really giving you more insight about the life in Pompeii. And here I wanted to bring a little bit more about the kind of some aspects of the technology that is used to know more about the city and especially the arts. And I'm going to show a few things about the artifacts that you can see here at the Orlando Science Center, but it's going to be shown with different aspects and different artifacts too. So that's why I hope you can learn from what we can do with lasers in archaeology and cultural heritage. And so for this, I'm just going to show you a little bit how we can survey cities with laser scanning. That's a technology that's really getting everywhere from our phones to our car. And it's used for all this scientific purpose as well. And then how we can analyze paints and art in general, both with molecular spectroscopy that we use with lasers, and then how we can even get information from atomic composition directly in the field, and we don't have to move the artifacts from Pompeii if we couldn't, or we can stay in the museum and not go in the lab. So first of all, I want just how can we survey the city and know more about the city itself and the buildings, and this is thanks to laser scanning. And so so you may have seen, if you have been to the exhibit, or I encourage you to go. This is a really great exhibit, and you have this nice reconstruction of a villa, and I really appreciated that there was this object there, because when we think about archaeology, most of the time we're all excited about the artifacts and the paintings, but we don't see much about the real life and like the type of houses and the type of life that people had like at the time. And so how can we know more about this aspect of it, like the topology, the structures in the city? This is something that is really interesting. And this is done thanks to, in part, laser scanning, and more technically and more precisely, one of them is terrestrial laser scanning. And so the way it works, I'm going to explain it very quickly, is it's just based on measuring distances with time. And so imagine, you can see here on the right, you can see that if you have so a pitcher, so that's going to throw the ball and wants to hit the wall, it's going to take some time for the ball to go to the wall. And so imagine you throw the ball and it gets the wall, and then it bounces back, and let's say the pitcher stays the catcher for this example, and then it's going to take here another amount of time. And so here, if you know the speed of the ball, so here, let's say in average, can be at 90 miles per hour, would be around like 40 meters per second. And the time between the throw and the catch, let's say was 50 seconds. That would be a very nice throw to last for 50 seconds. But then that means that you managed to get the ball to go from the pitcher to the wall and get back in 50 seconds at the speed of 40 meters per second. And so what's the distance that this ball has traveled? Is just you measure time times the speed, and then you have a back and forth. So the distance with the wall is just divided by 2, and you'd get like 1,000 meters. And so this idea of, I know the speed, and I throw something with that speed to an object, and I count and just measure how long it takes to come back. It's really what it is with laser scanning, and that's called the time of flight. We measure the time it takes to fly to the wall and come back. And so in real life, let's say, so this is how it works for the laser survey and laser scanning. And so you have this type of object, and here I'm going to show you just an excerpt of a video that shows how it works. So you see here, the balls are little pulses of light, like very, very short. And then what you do is just you send them on 360 up and down, and you rotate on 360 on a flat area. So you see, if you have a building, you can just throw those balls and they come back to the same instrument at a high speed, and you can measure how long it takes for each of those little pulses to come back. And so then it's just not only knowing like how far it is, but then you need to know where it is. And this is thanks to the technology itself in the instrument that allows you to know how far you are, and then the two angles, because you have those two mirrors to turn. And those two mirrors, well, they give you like an XYZ coordinate, and thanks to the time of flight as well. And so thanks to this, you can have like a very, very nice image. You can see in 3 dimensions an area around the instrument. And so if you want to do such a survey of an area, then you can even move your instrument everywhere you want. And usually the software that the companies are going to give you for this instrument are made to combine all those images together, and you can have a very nice image and a large, large area. And you didn't touch anything, you didn't bring any ruler, you just brought this instrument there. And this is all thanks to the fact that the lasers can provide a very directional pulse, a very tiny ball that you can throw at any wall. And so how was that used for Pompeii? And so one of the most impressive work has been done by the SciArc project. And so the SciArc project has done here, that was the forum, that was the Forum of Jupiter in Pompeii. And that was their very first project, that was to do a survey of the area. And I'm going to show you what they managed to have. And here, this is on from their website, you can have access to this image, but you can see here that they moved the instrument all over the forum. Of course, they didn't do that in one shot. But the thing is, then you can even zoom on some areas, you can rotate, you can really go in high details. You can see that when they took a measurement at one point, they even took a measurement, you can see at the bottom of the image, of another person who was taking another measurement. So it's very precise, and the more, I'm sure you've heard this, like the point cloud, but this is what everybody is talking about for driverless cars and the LiDAR as well. You create all those points and you recreate an image in 3 dimensions. So this is a very, very first exciting application of lasers for that has been used for Pompeii. And if you do this as well, like inside buildings, I can show you have very cool images, like you can see on the right. That was a work that's been done. I mean, that was published in 2019, where they did a 3D survey of baths in Pompeii and integrated several techniques, including laser scanning. And so here, what you could see is on the top, like the image A, you can see on the top that you have a lot more details, that there is no way you can use just a ruler or just pictures to do this. But, and on the right, you can even do virtual cross sections. You can really understand any hidden details that was not possible before that. So this is really a first application that was really exciting for the application of lasers. Another one is really how we can get more information about the paintings, and those at the exhibit, and you can see there's a lot of paintings, there's a lot of murals that are brought to you, and they're shown, and you see all those very nice colors, and you can learn a lot from them, especially with molecular spectroscopy. And the way we use the laser for it, I'm just going to talk about it in a little bit, but allows you to do identification of all those pigments and even knowing more if there have been, if there was some degradation and how they evolve with time. So you have like those two nice paintings or like paint on murals or fresco here on the right. But like, can we know more about the pigments and the paintings using lasers? And so one thing is, I'm gonna tell you more about like everybody knows the molecules but the molecules around us, they move. And here that was just, you have different aspects for the molecules to move. Like one is just, they can just move straight. They go from point A to point B, and that's called the translation. It's on the right. And then you have the rotation. They can rotate on themselves as well as vibrate. And here you have the three types of vibrations that can happen for a molecule made of 3 atoms. So it could bend. So you see like the black atom would be like going back and forth between the 2 red ones. You can stretch as well. So imagine just they go symmetric. So they extend together at the same time, they come back together at the same time, or they can go asymmetric, like the black one is going back and forth between the 2 others. But so how is that important for doing some analysis? And so the thing is that every molecule is gonna have a different signature, a different way of interacting with light, depending on the atoms that the molecule is made up of. So it's gonna be each bending, each stretching, symmetric or asymmetric, will be different for each molecule, the way it's made. And so we can use that as a way to identify what type of molecules are in a pigment or making up a painting. And so a very good paper that I wanted to show you here, just they looked at this room that was in Pompeii, that was the Ariane's house. And using lasers in general, most of the time, you can consider that they are non-destructive at all. So you just shine the laser on it and you look at the response that you get. So here, most of the time, the walls are gonna be made of different types of materials. So here you have like aragonite, calcite, albite, quartz, different type of compounds you will find on the walls. But then the pigments, they could understand that there was signs of sulfate salts thanks to those little signatures here. Each peak represents a signature of a type of vibration for a molecule. And when you look at all of them, you can say, oh, if I have, for example, here for aragonite, if I have a signature at positions 207, 702, and 1085, oh, that means I have aragonite when I interrogated this wall with my laser. And so you can go all over and you have those peaks. The intensity will tell you information how much there is. The position tells you what it is. And you can even see here that they showed that there was some nitrates that get formed. There are some sulfates that get formed after the fact, and showing the degradation of the colors into the wall paintings in this house. Then finally, I want to talk a little bit more about atomic spectroscopy. And this is, like Jesse was talking about, I did my PhD on such a technique. And so this is why I like to talk about it. And I'm still doing it here at UCF for chemical analysis. And as you may have seen in my bio, that's just, I'm doing forensic analysis as well, and we use that a lot. So how can we use that for anthropology and for archaeology? And so the frescoes are very good samples and to analyze with this technique of atomic spectroscopy. So exactly what is atomic spectroscopy with lasers? So how do the laser play a role here to do atomic elemental analysis? And so this technique here that I'm going to talk about is called laser-induced breakdown spectroscopy. I think the name itself tells you exactly what it is about. Just you create a breakdown, so you remove a little bit of a material, like you can see here, thanks to the laser, so laser-induced breakdown, and you look at the light that this little ball of plasma, this ball of light, will give you. And here in the center, you see that's an example of the type of signal you get. So if you have like this signal, it tells you as a function of color. So here, just to give you an idea, between numbers like 400 nanometers and 700 nanometers, this is the visible region of the spectrum. So you would see with your eyes any color that's produced here, but you see there's a lot of information below it. That's in the ultraviolet, and then even in the infrared region. And so this little plasma here, this little ball, has all the information in it to characterize the target that you interrogated with. So you can see there's a lot of peaks. I mean, this is very complex, and it's been always a nightmare for us to really train people to understand how it works. But imagine each of them, every element that you have in the periodic table, each of them has a set of peaks. Like I was telling you for the molecular spectroscopy, you have the same here for atomic spectroscopy. Every element will have a set of peaks at some positions in the spectrum, and that will give you a barcode. And you can imagine if I see a barcode, like the first one, I know there is sodium in there, and so on and so on. I could have another one give you aluminum, and then calcium, iron, whatever it is you can find. Of course, not as simple as having them separated. You have all of them at the same time, so it looks like a big mess of peaks. And imagine you have like, if you try to superimpose two barcodes and you try to get the price of it, and you will never be able to do it very easily. So there's a lot of data analysis that goes behind it. And this is the research that's still being done. But you get an information about all the elements that are in this target or in this painting. And so you can bring this into the field. And here is an example. You see on the left, there's what we call a handheld LIPS system, laser-induced breakdown spectroscopy. We always call it LIPS. So this is a little instrument. In this little instrument, that is not bigger, but I mean, you see the size of the handle is really the size of the hand. So it'll be like just 2-3 times the size of your hand. It's very, very light, like few pounds. But then in this, you have the laser, you have all the optics to make sure that you can create this little plasma, collect this light, analyze this light. You have the software, and it tells you everything that's in it. And so I want to show you like live what it would look like. And so you see, you can have a little camera like for this system, and it does this little ball of light, and at the same time collect the light, analyze it. And so you can scan a large area. This large area here is like few millimeters by few millimeters. So this is why we can consider we barely see the effect of it on a painting. And then depending on the different signals, you can have the list of all the elements that are in it. And so this is a very, very powerful technique to know more about paintings and frescoes. And so here, one thing I wanted to really bring to your attention is this work that was done to analyze a fresco in Pompeii. And they wanted to know more about this little part on top of it. They wanted to know what was the different layers that made up the painting on it. And so I told you, you just send a laser pulse on it. And so you remove a little bit, you create this little ball of fire, but you look the light off. But then you can stay on the same spot and keep digging and digging and digging. And then what you can look at is the different chemical composition layer by layer as you dig deeper. And so here in this paper that was done with some friend of mine that I haven't seen in a long time, but very interesting work that they do is just they go deeper. You see here, they go from just the surface and they go 5, 10, 15, even like 30 different layers thanks to the laser. And they can see that there are different layers inside the fresco for the analysis of their painting. And so the first layer, for example, had a very low concentration of silicon, magnesium, calcium that made up those pigments. And then you had, for instance, calcium was high for the second layer, and then lower in the third layer, when silicon was intermediate for the second layer, but higher in the third layer. And you can see all those, like the stoichiometry and the atomic composition. So you can really see each element that made up this, this type of paintings. And so I think here, I wanted to just, I think I'm going to be quite done, and I'm really excited to answer all the questions that everybody is going to have. There's so much more we could say. We stayed just in a little bit of time, but I just wanted to show you just what is kind of the state of the art so far, even here now in 2021, what lasers do for chemical analysis. And I'm really excited to answer your questions. And then I give the floor to the host. Then thank you again.
Yeah, thank you very much. That was an incredible presentation. Thank you for taking the time to join us today. I am very excited to know that we live in a time where you can have a handheld laser that will give you the atomic makeup of a 2,000-year-old fresco. It's just like incredible to think about. Again, thank you for sharing your experience and your expertise with us. We'll be back for the question and answer session with Dr. Baudelet after a short message from Tasha Dupre, Interim Dean of UCF's College of Sciences and an Orlando Science Center board member. We'll be right back.
Hello, I'm Tasha Dupre, the Interim Dean of the College of Sciences at the University of Central Florida. We are excited to have once again partnered with the Orlando Science Center to bring you some very interesting and informative talks given by our faculty from the college and educators from the Orlando Science Center. We would like to thank you for virtually attending the last of our Lunch in Pompeii speaker series, hosted by the UCF College of Sciences and the Orlando Science Center. We encourage you to come to the Orlando Science Center and visit this amazing exhibit firsthand. The exhibit will be on display during the Orlando Science Center's normal business hours until January 24th. Now please stay online for the question and answer session with our speaker.
All right, everybody. So we're back with your chance to have your questions answered by Dr. Baudelet. I'll start with a few myself. It'll give everyone a little bit of time to get their questions into the Q&A feature on your screen. Let's see. Yeah, you can also upvote questions. If you see a question that you really want to see answered, you can upvote that question. So, okay, Dr. Baudelet, you ready for a couple of questions from me? I've been really excited about the speaker series because of the partnership between the University of Central Florida and the Orlando Science Center. And I think those university science museum partnerships are incredibly important in any community. So I want to start off by kind of asking about informal education and science museums and things like that. So museums and informal educational centers like the Orlando Science Center are dedicated to inspiring lifelong learning and sparking an early interest. Have you had any impactful informal education experiences that you feel have helped you set you on your path?
Well, for sure, like the formal education has been like the most influential one. But I remember when I was a kid, and it's just the planetarium. That was like one thing that really amazed me, and I wanted to be an astronomer until until the time I had to choose my PhD, and I realized, well, maybe I won't have so much of a job after. There's not many astronomers, but so I moved. But the thing is, the planetarium was really the thing that made me see the wonders of science and what we can do, and then I was lucky that I could even just like live in an area when I grew up that nature is omnipresent. I was not living already in a very urban environment. So just that helped a lot in seeing all this. And I think those are like the two most influential aspects that brought me to science. Yeah.
Yeah, that's wonderful. Planetarium visits were one of my favorite experiences as a kid also. And I actually was lucky enough to run planetarium shows here for a little while. And that was extremely fun. I loved it. Okay, how about when we talk about getting involved in a STEM career, I'm just wondering if you have any advice for anyone who might be interested in studying a STEM field in college.
Well, STEM now is like, the definition of STEM is so broad that you cannot just give like one advice. I mean, one that I have is just what I lived myself. That is, don't get stuck to one thing you think you want to do. And my PhD is in physics. I did my postdoc at UCF in optics. Now I'm a faculty in the chemistry department. I do forensic analysis. I work very closely with anthropologists. I think it's just STEM in general, just be curious and just never think that you know what you want to do. And this is maybe the first advice is just, and then sometimes you get stuck. I mean, sure, it's not easy. The science is not easy. I know that many people get stuck with physics or like mathematics. And just, I know because I've lived that at home. It's just, I love it. My wife, she's not that much into math, even she loves it, but she gets frustrated very easily about this. And I try to explain it, but this is hard. This is very hard. And this is something that I love though. It's just people being so attracted to it. And this is the thing, talk to people. If you're lucky enough to have like a father, a mother, a brother who's in STEM, just go and just bother them and just like go for it. Ask questions, be a real pain until you have your answer. This is really this. It goes with the curiosity. It's just never stop asking questions. And that goes with life too. Never believe things. Always make sure you have your own judgment. And we've seen what it has done in the late years to just believe things. You want to make sure, be curious and be sure you have your opinion.
Yeah. Well, that's absolutely a fantastic answer. I totally agree with you. Just asking questions all the time. And when I see guests out on the museum floor investigating dinosaur fossils or space science or something like that, the ones who are having the most fun and getting the most out of the experience are the ones who are just asking questions endlessly, you know?
Yeah.
So I totally agree with what you're saying. We do have some great questions that have come in. I'm going to go ahead and get started with our audience questions now. Just right before we do that, I just wanted to show you this. It's a new style of program that we're working on at the Science Center.
Yeah.
We've used, we took an old Xbox Kinect that scans you as you're playing games and stuff. We're able to scan some of the employees here and then make I don't know how well this will show up. Let me see if I can do this. We made little 3D models of some. So this is Spencer. He works here. You might see him on the weekends if you come to do shows. But we were able to, scan Spencer, make a 3D model, and then actually print it out so I can keep it on my desk. It's very cool working with lasers and stuff.
Yeah, we have the same here in my lab. It's just like, that was maybe like the first thing that we've done. I was like, oh yeah, let's scan somebody in the room and then print it.
Yeah. Okay, so we have some great questions here. So the first one is actually something I'm very interested in the answer for this. So is there software that can take a laser scan and kind of add or fill in areas in the scan in order to create a likely original structure where sections are currently missing?
Well, yeah. So I think it's even like the basic software that's given by the vendor if you buy like a laser scanner. So there are different things. It's just I'm sure you can always ask how much you want to interpolate. You know, it's just either you want to be very conservative. So I don't have a data point, so I don't want to see it. But you can say, well, based on whatever's around, give me a smooth image. Like you see, if you have like a wire, like, or just like you have something that blocks the path of the laser, but most likely that could be just from like the wall behind it is going to be continuous. So the softwares now are very intelligent. There's a lot of artificial intelligence now that goes into this. And like I was saying, it's just like they never take one position. So they take one, they take another one, and all those instruments work with GPS as well. So they know exactly the positions and they can make the calculations which point from one position goes with which point of the other position they took the measurement, and they know if this is the same point. And so this is all about geometry. I mean, if you think about it, it's very complex geometry with like billions of points, but the softwares themselves now do it very easily. And this is why sometimes you see those smooth 3D modeling of structures. Yeah.
Yeah, man, we live in cool times, you know? How about, did you laser scan individual artifacts as well, like cups, pottery, etc., or and if so, what is that process like? How do you scan something like that?
So I have not, because this is not my research, and I'm sad I've never used a laser scanner really per se, besides the one in our 3D printer. But this is exactly the same thing as for your colleague when you took the 3D scan for the 3D printing. You know, it's just usually you let either the laser like turn around the object if it can fit in an area. But I didn't show it, but there are companies that they sell handheld laser scanners that you can reproduce the 3D image of something. And this is all based as well on, I know where the laser is, I know where the object is, I know where the hand is, I know everything about the geometry. And so then I can go around, I can go inside. You should ask my colleagues in archaeology for sure to know how much is used for like pottery and small items. I don't know how much it is used, but usually it's used a lot, like even in anthropology. And there was this talk in the series about like people, like the bodies and like fleeing Pompeii, but you know, like working in forensic science, there's a lot of work done in 3D scanning as well for bones and whatever we can see on the scenes. But like now there's like you said, we live interesting times. There's like the laser is not just, you know, it's not like a big box that's in a lab, and it's just, this is in your phone, this is everywhere. You can have small handheld systems that will help you, covering all those little items. Yeah.
It is very there's something so fascinating about a staff member standing on the floor just kind of randomly scanning a guest with an Xbox Connect, and then their whole head shows up on the computer. It's just amazing.
Yeah.
Okay, so how about this? We get this question, I think, all the time when we do these speaker sessions. It's like one of the best questions to ask, but it does put you on the spot a little bit, okay? What was your most unexpected finding in your research? What's the thing you've been the most surprised about?
Wow.
Yeah, see?
That question? No, it's, okay, so maybe it's not just once. It's happening a lot of times. It's just, wow, it works.
Mm-hmm.
So you have an idea, you say, yeah, I mean, it should work. And then you always expect like this, yeah, that doesn't work. But sometimes it works the first time. And this is like the most exciting one. Lately, and in my research, I work with like pollen grains and things like that. And we just published about it, that we could measure DNA from a single grain of pollen just without destroying it. And honestly, I wanted it. I wanted it so bad. And we made it happen so easily. I was like, wow. And that goes back to the advice at the beginning. Never stop yourself into like trying things and asking questions. Just try it. I mean, you never know. And this is something that I've seen a lot of students I've worked with and colleagues. And sometimes we think that, oh, this model is going to tell me if it's going to work or not. And it's going to take 2 days to tell me this. And I remember another student say, yeah, during those 2 days, I'm going to try it 20 times. And I'm sure I'm going to find things that work, but you cannot even think about. Yeah. And this is really this. I think this is the answer. It's just like, wow, it worked. Yeah. It's just
yeah, that's great. I taught for a few years in a science lab for elementary school students, and they would get very upset when the thing that they tried didn't work out the first time. And I tried to explain to them, that's not how it works. It's going to take a while to get used to it, because when it does work for the very first time, you're going to be so excited and you're going to jump up and down, right?
Exactly.
Yeah, it feels so great when something like that happens. All right, let's see. As I remember from our graduate optics and photonics classes, to induce plasma from the surface for atomic spectroscopy requires laser beams with a very high peak power. Are there any ways to minimize the damage to the archaeological artifacts caused by such intense laser pulses?
So, yeah, so here I'm going to play a very political answer, but it's like, what do you call a damage? So, sure, if I look at a fresco that is like 20 meters by 20 meters, and I do just a little spot that is 100 micrometer in diameter, it depends who you talk to. Some are going to be, oh my God, you destroyed it because that was sacred. And some are going to be, well, okay, I pay the price of this 100 micron spot, but at least I know information about it. But to minimize the damage, usually what you do is just, and this is what we try to do anyway, is you look at the minimum power that you need to just get the signal you want. And I didn't show it here, and that's a technology we use in my lab as well. Here, you want to have enough power to remove a little bit of material and make this little ball of light and this plasma. That requires a lot of power compared to just removing and not having enough to do the ball of light. You can still do chemical analysis, but for this, you cannot do it in the field. You have to bring it into the lab. So you just you imagine when you're with a little X-Acto knife or a scalpel, and then you remove a little bit of the paint, put it in a little vial, and then bring it in the lab. You can do that with lasers. So you don't need to go so you can just remove a little bit, catch it into a vial, and then you bring it in the lab. So you can do that. There's going to be way, way lower damage for sure.
Yeah. All right. Well, and then you have to work, I guess you work closely. I don't know, I guess if it's a museum or an organization that has the artifacts, you just work closely with them and they kind of figure out where they'd be most comfortable.
Of course.
And all of that. Yeah. Okay. Very interesting. How about, was any lead found in the frescoes or any other unusual elements?
I do not know. So
yeah,
I didn't do the studies.
Right.
I mean, lead is an element that is in a lot of pigments, especially I think white pigments have lead in them, if I'm not wrong. But so I wouldn't be surprised lead is discovered. Yeah.
And then this question asked, how does the atomic spectroscopy analysis translate into the various colors that we see?
Wow. Okay.
Yeah.
So every chemical composition, atomic or even molecular, like we've seen, like with the molecular spectroscopy. So you see, like I've just mentioned, like, well, I bring a laser on it and then I see the response, right? But the light that you get from the sun, or even from the light you have in your room, is just then it's going to just bounce back on that surface as well, right? And what you see is just all the light that was not absorbed. Okay, so depending on the composition of your material, some colors in the white light of the sun or the white light of the light bulb you have will not come back to your eyes. And so, for instance, if you have, if you remove most of the orange part of the spectrum, you're going to see blue. And so then any pigment that shows that it's blue means that it absorbs most of the orange part of the spectrum that you have. And this is how you can relate chemical composition in general with the colors. And so that's a very interesting question, because I don't know if you remember, that was like the big dilemma years ago. That was what's the color of that dress, and that was like people were saying, oh yeah, it's like blue and black, and the other one was, no, that's white and gold. And I think that was like this year, or I mean last year, there was like the same thing with like Billie Eilish shoes or something like this. And it was like, what color is it? And then the whole internet was on fire. Just like, that cannot be that color.
Yeah.
That's exactly this. It's just, well, I can make anything look like any color. It's just, it depends how much light I remove from the start. I mean, we can go with the extreme, right? It's just, if I look at an object in pitch dark, I will see everything black. Yeah. If I look everything with a very bright white light, but I'm going to be blinded by it, everything is going to look white. But then it's just, if I remove the blue, let's say like the example I had with orange and blue, to see something blue, I need to have blue light coming to my eyes. So let's say if I shine a blue object with just orange in it, with just light with orange, there's going to be no blue to come back to me. And so it's going to look black. So this is why the chemical composition is important, but the lighting is very important. And I know this is something that is, it's crucial for museums, like to work with what's the proper lighting to show all the images, all the painting the way it's supposed to be. And you look at a painting outside, or you look at a painting inside, it's going to look completely different. There's going to be details you cannot see outside, or you cannot see inside, because there was not the proper lighting. And it's all about this. It's all about like interaction between light and molecules that's going to define the colors.
Yeah, our observatory right now is closed because of it's not totally safe up in the observatory right now, but once it is safe, we'll have it open again. And what we've been doing is we run a spectroscopy activity where guests can look at elements, and then if they have like the light signature that they can see, they put on like prism glasses, basically.
Okay.
And they can see like a basic version of how the light is different for each of these elements. And so I would encourage everybody, when it's safe to open up the observatory, come on by and check it out yourself.
And a good example too, to understand colors and chemical composition, look at fireworks. It's just like every firework has a different color because it's a different type of salt that's put in there with a different element. This is the first manifestation of it, if you want.
Yeah. We also have a show where we blow up balloons filled with hydrogen, filled with the chemicals that are in fireworks, so that we can see those color changes. Yeah. I want
to be there for that.
Yeah. Oh, it's a good time. All right. Let's see here. Do you know of any work to use laser analysis on art to detect forgeries? Have you ever heard of anything like that?
Oh yeah, there is. And so usually the thing that's very, the idea behind it is that the chemical composition of a forgery can be different from the original. And if we talk about paintings and colors, all right, so with colors, the thing is you can create the same color different ways. And so usually you can imagine, I mean, this is kind of easy. Sometimes you cannot recreate the same pigment as was used in Pompeii. You cannot do it now. It's just, you don't have the same materials to start with. And so it's going to be very easy to know the difference. It's going to be very easy to look at what was used in Pompeii because you have other artifacts and you can base your knowledge off. And then you have the new one. It's going to say that thing couldn't exist at the time of Pompeii. So I know that's a forgery.
Yeah.
So yeah, usually this is the way it works.
Very cool. Let's say, how about, can the lasers be used on, this question is asking, can the lasers be used on inorganic materials, and would they burn up, like, let's just say, like tissue, like human tissue, or if it was used on skin or something like that, some organic material?
So yeah, I mean, it can work on everything. I mean, if you hit hard something, you're gonna make a hole in it. It's just, you just need to hit hard enough. So with tissues, you have a lot of issues with the water content, for instance. So that takes a lot more power from your laser to make it work. But tissue and like biomedical studies using lasers, it's done every day. I just come back from France where one of my best friends is doing this kind of every day. And he makes tremendous images. It's just, if people want to see what he's doing, just please send me an email. I'll just send you images and links to what he does. Yeah, so you can look at everything. You adjust, like I was saying, if you want to use the technique that I showed, lips, to make this little ball of plasma, you just like use the dial, you know, just like, well, I need a little bit more power because it's going to be not as easy to make this ball of light. Metals are super easy, biological samples less easy. So I just crank up and I get my light. Yeah.
Oh, okay. Let's see. How long has laser technology been being used for the purpose of, let's say, any of those topics that you discussed in your presentation? And what year did it begin? When did we start using lasers to analyze things like this? And do you know, how has UCF been involved with the use of lasers for analysis?
So when did it start? So laser was what? Now I'm going to be, everybody's going to just listen to me and I'm going to be just like hang if I have the wrong date. I'm always between 1960, it's in the 60s, between 1960 and 1965 is when the development of the laser happened. And from the time of the publication / patent, that's another story. The thing is, I think a year later, 2 years later, the first thing people did was blow things up with lasers. That was the first thing. It's just like, well, let's do it. And that's funny because I wrote a paper on this on the first years of LIPS, the five first years. And that was really in the late 60s, early 70s. And that was done, of course, with the labs that could afford a laser at the time. So that was like national labs or very big companies. But 2 years later, and what I consider one of the first papers written about laser-induced breakdown spectroscopy was by 2 French women. And they just borrowed, they went somewhere, like they had this lab had a laser, they went there, focused, run a lot of samples and look at the spectrum that it was given. And for me, this is kind of I always want to say that's the first LIPS paper because, well, they're French and they were women. So that was great. And the story behind it was very interesting because this work was presented at the Academy of Science at the time, but they couldn't present it. So that was a man that presented that work. But the thing that is funny is just the name of this man is just at the bottom at the end. Nobody cares. It's just the name of the 2 women were like really up front. So that was a good thing. Yeah, so really early, as soon as the laser started, so in the late 60s, we started looking at interaction. I was not even born, but the thing is, like people were saying, okay, what can I do with this? Because the laser is something that's funny. It's easier to make a laser than find an application for it. So there's a lot of people just, I made this laser, what can I do with it? It's just like, you have the wrong person. I'm the one, like, I will want you to build the laser I want, and usually you can't. So it's just like, it's always like, I made this laser, what can we do with it? And so very early, people have seen like molecular spectroscopy could be done with the Raman effect. That's what I presented today. That Raman, even if the effect itself was not discovered with the lasers, but they discovered, well, I replaced my lamp with a laser, I have way more signal. So let's do it. Then blowing things up for sure, and making plasmas and looking at the light. That was like the first thing. And then it goes into way, way more complex analysis where the light is not just, it's not just about like having light hitting a sample. You're looking at a very, very deep, complex interaction with like phase and intensity and polarization, and you combine 5 lasers together to try to get an effect and seeing something in details. And to answer the question about the involvement of UCF here about like lasers for analysis, there's a lot of things going on. Well, I'm part of this. That's what I do. There's the College of Optics, of course, but some of the faculty there do some chemical analysis, and with very like those complex ideas, how to interact samples with lasers, they develop those. In engineering, there's a lot of people as well. In chemistry, we are like a bunch as well. Yeah.
You see the importance of scientific breakthrough. So lasers happen, and then physicists are interested, chemists are interested, and then all of a sudden, an anthropologist is interested, and a biologist, and someone studying the ocean to scan the floor of the ocean, and it just becomes this really broad thing that everyone starts to use when they find the right application for it. So, Dr. Baudelet, I want to tell you, we only have about 3 more minutes.
Oh, yeah, okay.
I have maybe 1 or 2 more questions here. One here says, I would like to know how expensive is a laser analysis compared to other underground imaging techniques and technologies. And then also, I'm not sure how much you would be able to speak on how they decide to make the imprint on the painting. The area where the libs is focused on is tiny, but how do you pick what part of the portrait you would hit? So just again, how expensive, and then comparatively maybe how expensive, and then how are you deciding where you would scan?
So how expensive, it really depends the technique you use. And honestly, the thing is, the price is always going down. And now you have lasers in your phone, and there's more and more stuff going on. So from five figures, now we start going to 4 to 3 figures for some instruments. So that's very, very exciting, because then more labs can do it and more people can do it, and we can introduce it to schools because it's cheaper. So it really depends the technique. I mean, I cannot give one price tag on this. Then after, how do you decide? Well, usually it's not someone like me that's going to decide. That's going to be the person in charge of the artifact. It's going to say, well, either you really want to know that point. And so you're going to find all the techniques before having to remove a little bit. And there are a lot of techniques you can kind of do what the laser does without destroying, but it doesn't provide you all the information. So it depends what you want to do. Or you, like you were saying at the beginning, you try to go somewhere where nobody's going to see it, and that's going to be okay.
Yeah. Well, I just want to thank you again. This has been absolutely fascinating. I've had such a good time talking to you. Presentation was really fun and interesting. And again, I would encourage everyone to come by the Science Center to see Pompeii before it leaves on January 24th. I do want to say we had a few more questions that were in the chat, and I would encourage people with have permission to do this. So you can email Dr. Baudelet any of your questions, and when he can, he's going to get back to you with those answers.
Yeah, I'd be happy to. Yeah, that'd be great.
Yeah, that would be super nice. Thank you very much. It's really wonderful to have a scientist that you can just directly communicate with. So once again, thank you very much for doing this. I appreciate everybody joining us. I hope everybody has a safe and wonderful weekend coming up. Have a wonderful day, everybody. Thank you.
All right. Thank you.